Good morning. My name is Subhojit, and I handle everything technical in Abundance AI. So thanks again for coming to this talk. And firstly, a note of thanks to the organizers. The intent of this talk is to share my war stories in deploying large Spark models, especially for real-time use cases. Initially, I'll be just starting off with a little bit of 3 to 4 slides of context, and then I'll deep dive into the demo and the more technical stuff. So big data is not easy. I apologize for the term big data. Let's, for our definition, say data that doesn't fit into a single node. And the reason big data is not easy is because it sits at a confluence of 3 different diverse and very deep fields: machine learning, distributed systems, and domain of business understanding. And now you want to mix and merge these 3 different fields, very deep fields, together to make business revenue. And that is quite a challenge. Gartner found that just 15% of companies have machine learning models in production. The key word here is production. And the top 5 vendors in the big data space are all in losses. And 90% of all data lakes fail. So that is something that needs to be addressed here. Why is this happening? Gartner, again, tried to find out why this is happening. The first 2 reasons that you see here are very organizational. Because this is a new field, organizations still have to figure out a way to get value out of big data. And then most companies are not structurally set up to get or feed the data out of silos. But this talk is not about the first 2 points. This talk is about the last point. How do we address the issue of agile model development and deployment? Generally, when we look at media, we always talk about this part, the machine learning code. However, when we look into production machine learning systems, we have to talk about the entire thing here. You have to talk about configuration, data collection, feature extraction, data verification, process management tools, serving infrastructure, A/B testing. This is your entire pipeline. However, the media just concentrates on the ML part. This is just 5% of your code. And the remaining, if you have to push this machine learning code into production, you have to write the other part of the code as well. And that's 95% of the code. To explain this entire problem and the solutions, I'll be walking you through a use case that I had. I was working with one of my clients, and at that point, I faced a few issues because that was the first time that I was deploying something into production. And the way I structured this presentation is I'll first talk to you about the business use case, what the issue was from the business side. I'll talk to you about the first solution, the problem faced with the first solution, a better solution, demos. Then I'll conclude, and I'll take questions after that. So key takeaways. At the end of this presentation, hopefully you guys can take this with you. A better than random model has revenue generating propensity from day 1. Now, I'm not talking about medical grade machine learning models. I'm talking about business models. In a medical grade, possibly you want to have a ROC of more than 0.9. But for business use cases, a better than random model from day 1 has revenue generating propensity. So there's no need that you need to keep that inside your own laptops and not push it into production and expose it to the world. The second thing is PySpark models can be deployed in a Scala pipeline. Now, this war going on between data scientists and data engineers. Data scientists want to code in Python, and the data engineers would like the type safety of the JVM and want to push that same machine learning model in a JVM-based pipeline. So what happens there is once the data scientist meets the goal of metrics. It is the poor data engineer who has to recode the entire machine learning model as well as the pipeline to push it into production. And what happens during this time is when they push the model across the wall, a lot of this assumption just falls apart. And for a long term, it's not a sustainable solution. So one of the parts in my demos would be, how can you ensure that you build a model in PySpark with very minimal code changes, you can use it in a JVM-based pipeline. The third thing is PySpark model can be scored in real time or in near real time. Spark is very good for batch processing. However, the distributed tags that Spark has, that is also the problem that stops it from being used in near real time use cases. We'll go over how that can be solved. Spark models can be Dockerized. Now, today, Docker is a unit of scale. If you can Dockerize your machine learning model, you automatically get the advantages of CI/CD, metrics, scale that the web application world has already figured out for you. You need not reinvent the wheel once you push your models or convert your models into a Docker container. And all this can be done in a matter of minutes. The entire pipeline can be done in a matter of minutes, and I'll show you in the demo how this can be done. And the GDPR is already in force in Europe, and you need to take care of personal information. And one of the themes of this talk would be using GDPR compliant features. It is possible to get good, accurate models. So, business use case. Roughly last year, business came up to me and said, hey Subhojit, we have this website where we sell products. People come to this website and they buy these products. Is it possible, before the session of the user completes, can we identify the intent of the user, whether he's going to buy a product or not buy a product? So that the business could actually show them discounts or change the intent of the user by giving him certain offers. So that's the business use case. If we dive down into the business use case, it is a real-time segmentation or classification problem. What makes it a little bit more tricky is we have to be GDPR compliant. In academia and in business, we already have models that do a real-time segmentation. However, most of that uses your personal information. For anonymized data, to get a model on anonymized data and expose that in real time and that model being built on gigabytes of data, that makes this problem non-trivial. But first, to actually create a model on the real-time data and act on that real-time data, we need to collect the data, right? So the tool that I chose is an open source tool. It's called Snowplow. How many of you have used Snowplow before? Okay, so Snowplow is basically an event collection and enriching tool. You can hook this up to your website, to your mobile apps, and in real time you can get the events as they are happening on the website or on your mobile app, and you can collect, transform, and store the data. Now, each of these are separate building blocks that can be scaled. And each of this is a completely scalar-based platform, so you could go under the hood and change it for yourself. For this use case, I have used Amazon, but you could use any of your the cloud service providers that they have, and you just need to change or replace the building block with the building block that's available on cloud or an open source tool as well. So this is your standard Lambda architecture for this. So whatever you're seeing here is being mapped to this Lambda architecture. Lambda architecture, for just to give a brief overview, it's if you want to aggregate data in real time as well as take advantage of your batch data. Lambda architecture gives you a good way to aggregate this to information. So what you see here is basically the data coming in from your website or your apps. It's collected in the stream collector. The stream collector then sends the data to Kinesis. You could replace Kinesis with Kafka. And from here, there are two paths that these events take. One path is for the real time, and the other is for batch. For the real time, the data is actually verified in a real time basis with a schema registry. In Snowplow world, it's called Igloo server. And given whether the event is good or bad, each of those events are sent to the good event stream or the bad event stream. And then you can hook up your dashboards to these streams so that you can in real time see what's going on. The other part of the pipeline is the batch part, where the data, the events data, gets replicated to your S3 or your permanent storage. And then each of that data can be used, or the files can be used for batch processing and evaluating and creating models that you can use for later mapping of that to real-time use cases. A little bit about the production numbers. So this is the numbers are a bit stale. This was when the project actually started. So we had about 23 million events per day. We collected about 140 gigs of granular data. And the entire cost of maintaining the pipeline was 6 to 12 euros per day. And also, most of this, because it was using managed services, we had very limited need for a full-time data engineer who would maintain it on a 24/7 basis. Fine, we created this pipeline. How does it perform? So I performance tested this just to see the latency requirements and also to see how these are performing in real-time conditions. And if you see, the 99th percentile of this returns in half a second. So which seems to be a pretty good metric to get some confidence and get things started off. So now that we have the real-time pipeline, can we train and score our ML model? That we are getting the events. Can we hook up our, using these events, can we train the model so that I can use it for real-time segmentation? So the first model that I selected was a Markov chain. Remember that I was using, the most important part of this use case was I had to build the model on anonymized data. I cannot use personal information. So what I did was I took the sequence of the web pages visited by the user and created a Markov chain model on that. Very quick and fast way to create a model and check if this actually makes any business sense or not. So I created this model in R. I uploaded it to S3. I exposed it by the AWS Lambda, which is a serverless framework. And then I exposed it to the external world through the API gateway, right? It's the happy path. But it's not so happy after all. AWS Lambda, it's very good for serverless. You can scale. It's very cost effective. However, when I first created the Markov chain model, I had to hit 212 MB of the model size. And AWS Lambda needs 50 MB. So have you hacked on the core R models on a weekend? I wouldn't recommend you do it. Unfortunately, I had to and got that down to 26 MB. So good for me. I can now use AWS Lambda and serverless. That's problem one solved. Problem two, R is not supported in AWS Lambda. So I had to create a Python wrapper around it. That worked. But then the final nail in the coffin. Every time front end would change, my model would be no longer valid anymore. and I had to train it again. So you would hit the typical cold start problem. So obviously, there was a need for a better solution. But what are some things that were learned during this process? We had seen serverless being used in web application world. However, using it in the machine learning world was something that I was trying for the first time. And so it was well worth the effort to see serverless being used. And I've been a big fan of John McCarthy, sorry for the name dropping. This gentleman, somewhere in 1961, had said that the computer systems that he had advocated, and he was talking of time-sharing systems, if people would use it, someday computing would become a public utility. So they would switch on, use it, and switch off, and you would only pay for the compute that you use. Something like you use for electricity, or say, for example, tap water. Yeah. And it was pretty nice to see it live, what the gentleman thought about and what you're seeing. John McCarthy, if you, there's a small trivia about him. He was a Turing Award winner and had married 3 times. There's no correlation between the last 2 points, though. So, better solution. So the better solution here was I had to decrease the time for the models to move from notebook to production. That was the requirement number 1. It had to be agile. It had to be super scalable. So one of the nature or characteristics of clickstream data is it just grows and grows on you. If you have to create a model on that, your machine learning pipeline, your modeling framework should be able to handle large amount of data. The third thing is it had to eliminate recoding of the Spark feature pipelines and models. So once I build my PySpark model, I should be able to take that model and deploy it into production with minimal code changes. So that was point 3 for me. And the serving and inference of these models had to be super fast. Now, this is a real-time use case, and I need to meet the business requirement, I need to ensure that these models can serve the business requirement in real time. So these were the 4 requirements I had. So let's deep dive a little bit into the technical requirements a bit more. So for model serving to be super fast, it was clear that it had to be outside the realms of Spark context. Now, Spark has this distributed tags. It's very good for batch processing, like I mentioned. However, for real-time use cases, it doesn't serve your purpose. And you need to get your model, your Spark model that you created on the terabytes of data out of the Spark context in order to expose it in real time. So that was challenge number 1. The second thing was it had to be completely vendor neutral. So if I build my model in my own data center, I should be able to expose it in AWS. Or if I build it in AWS, I should be able to expose it in GCP. So it should be completely vendor neutral. And the true test of serialization or portability is, can I zip up the model that I created, email it to my coworker, and can she use it on her environment and serve incoming traffic from her environment just using the serialized model? So these were the 3 technical requirements I had. So coming to describe a little bit about why Spark is slow in scoring, or not that good for real-time use cases. When you get the data, Spark creates this DAG. This is a directed acyclic graph of how the data looks like. It creates this lineage, and it creates this execution plan. When you have terabytes of data, this is fine, because this cost, this distributed tax, gets amortized over the entire gigabytes of data. However, if it is a real-time use cases where you have a single row of data that you're scoring on, all this sequence, the creation of DAG, the lineage, has to be done, even for a single row of data. And for one row of data, possibly you don't need to pay that distributed tax. So In order to get the model out of the Spark context, there were a few tools available in the market. I had a few metrics by which I had to evaluate each of those products. Finally, I chose MLeap. And the reason was, for me, it was important that the product supports Scala and Python. It had to serialize out the entire pipeline, not just the model, but the pre-transformations, the entire model building, the post-transformations, the entire model I had to get out of the Spark context. So the only tool at that point that was available to me that was open source was MLeap. Just as mentioned, Databricks also had a product called DBML local, but that was proprietary at that point and it was not open sourced. A little bit description of MLeap, what MLeap is. MLeap is possible because of the good work of Holland Wilkins and Mikhail Semyonik. So what is MLeap? It's a common serialization format and execution engine for machine learning pipelines. And it allows you to completely serialize the model, the pipeline, the pre, the post transformations, estimators out of your Spark context into a serialized form. It supports Spark, scikit-learn, and TensorFlow. And once you serialize the model out, you can deploy it onto AWS, GCP, any wrapper that you have. For most part, you don't have to modify any part of the code. It's mostly plug and play. But because it's open source, you can open the hood and you can actually change the part that you would, especially on the serving side, or while creating new transformers. In fact, I had to change a part of the code, and if I have time left, I will show you that part as well. It's completely open source, and it's Scala-based. To give you a visual representation of how MLeap looks like, you have the data layer where you have the raw data, and you have these processing engines. You have Spark, scikit-learn, and TensorFlow. On top of this, MLeap creates this MLeap bundle. This bundle is the format or the internal format of MLeap for serialization. So the rationale here is if you are using say a string indexer, the compute or the mathematics behind each of this, whether you're doing it on Spark or in scikit-learn, is the same. So why not have a serialization format or have code that sits in between all these multiple frameworks? So that's the rationale. And then once the bundle or the serialized model is out, you have something called as the MLeap runtime. So the model is in an MLeap bundle format. Once it's serialized, you need something to understand the new serialized format. Now, why would you need to do this? The models in Spark can only be understood in Spark. This bundle MLL has its own internal format. So the data frames in Spark, there's a corresponding data frame in MLeap world, which is called a leap frame. So individually, each of that, including the transformers, estimators, all of them get one-to-one mapping into this new environment. And to understand this, you need a separate runtime that can understand the serialization framework. So that is the overall picture of, from top to bottom, how it looks like. Further drilling down, each of those, the components that I showed you, this is, if you see the creation of the MLeap bundle and the runtime, so the core, the core here provides you the linear algebra library, the features, builders, the transformers, estimators. This part takes care of all the one-to-one mapping between your Spark world and the MLeap world. The runtime provides you a leaf frame, like I explained. It's your one-to-one mapping between your data frame in the Spark world and the MLeap world. Right? So it has your schema, it has your rows, and it maps how the data frame looks like. And then there is the MLeap serialization, which takes care of, once you get the bundle out, how do you serialize this model out? So that's the part that's been taken care by the MLeap serialization. One thing to note is the serialization is done in JSON and protobuf format, and the reason this was chosen was JSON and protobuf handles well with different environments. So this part here, let me just discuss a little bit about the bundle ML. So like I mentioned, bundle ML is a common serialization format for both Spark and MLeap. It's 100% JSON and protobuf format. And what happens is once you serialize the model out, it comes out in a zip form, and you can go inside the zip and you can actually see both the pipeline, both the nodes and the models, and you can see that this is in JSON and protobuf format. And I'll go over it while I create a model, and I'll show you it in the demo. And as part of the demo, what you would be seeing is I'll be building a model in Spark. I'll use MLeap to serialize the model out and then expose the model out as an API. So to make it more concrete, I'll be building my model in a notebook using Spark and Hadoop. The data would be on my own laptop here, but in production environment, I had to use it on Amazon EMR. And Spark would be using MLib to basically create the models. MLeap is going to create the transformers and serializers. And then using the MLeap API server, I'm going to expose that model out as a REST API. A little bit about the transformers and estimators that's available right now in MLeap. And the reason you would guess is, like I mentioned, every transformer, estimator, model that you have Spark needs a one-to-one mapping in the new ecosystem as well. So the good news is almost all the transformers, models, and estimators are available in the new ecosystem in the MLeap world. The last I checked, ALS is still being worked on. And if you want a custom transformation, you're just one git pull away. And it's pretty easy to do your own write your own transformers. The interesting part, the demo. So I can't use production data, but what I'll be showing you in the demo is the same workflow that I used in production. The only thing is I wouldn't be using clickstream data. I'll be using publicly available Kaggle data. And what I'm going to do is build a PySpark model on the Kaggle data in Jupyter Notebook. I'm going to serialize the model into a JSON and protobuf format. I'm going to load the serialized pipeline into a Docker container for near real-time model scoring. And when I tested it out, it was giving back in 50 milliseconds. With Spark, takes like close to 1 second to actually get that out. And serve the Docker container from a scalable REST API. So I'm going to do it on AWS, and I'm also going to show that on a Kubernetes cluster. Okay. So this is the notebook we have. This is for Kaggle. This is a Kings County Kaggle competition that was given some time back. You have data that's available. The reason I'm using it is because it's publicly available. You could actually see the workflow, and the end goal of this demo is not how to create the model, but once you create the model, how do you expose it out and serve it in a scalable machine learning API. So I'm going to rush over the data analysis part very quickly, and the place where I'm going to start this model is this notebook is once I have created the features, I'll be starting off with the Spark part. Okay. So this is a PySpark notebook that's running using Apache Tori in the backend. So it's using your PySpark SQL context. I'm using the PySpark ML models. I'm importing them. I've run this notebook earlier because I didn't want to waste a lot of time. And I defined the schema for the data that comes in.
Can you make it louder?
Yeah. Is this good? Yep. So I defined a custom schema for each of this. The data is basically, you have each ID, the property ID, you have the date of the listing, and you have certain features of that listing. Yeah? And the end goal of this is to basically predict the house prices. It's a pretty simple regression problem. So I read the data from the CSV file, and if you see the data frame, this is what it looks like. Yeah? I create the continuous, the categorical features. I create the train and the test split. This is a standard workflow. I use the one hot encoder, and I basically scale the individual features, the numerical features. And then I finally create a pipeline. Now this pipeline has been created. Remember, the end goal is just not to expose just the model. The end goal is to expose the entire pipeline, including the pre-transformers, the estimators, and the post-transformers as well. I create the model. So it's been created. And let me see if it's the model that I created in the Spark world. Can it actually do a prediction or not? So, well, it works. So now it's actually doing a little bit of predictions. Let me time the raw data frame that we have in the Spark world to see how and what the timelines we have on this. So you see this. This is a local data frame on my laptop, and it's taking 216 milliseconds. Now, 216 milliseconds on a local data frame, well, it doesn't fit quite a near real-time use case. What you would see is your data scientist or in your company would basically finish up till here and now hand over the model to the data engineering team to basically build this entire pipeline right from the starting to the end in Java. Now, this is something it's going to be pretty tricky for a data engineer who doesn't know much about data science to code in the Java world. But the goal of this presentation was to show you that they don't have to do that. In just 2 lines of code, you can serialize the entire work that you have done out and expose that in a Java pipeline. So all that you need to do is just write these 2 lines. I'm importing the mleap system and this simple Spark serializer, and I am creating the bundle jar and I'm serializing this out. Let's see if this is too small, I guess. Is this good enough? Okay. Sorry, I need to reduce the presence. Okay, so if you see, there is a PySpark lr.zip that's been created right now at 10:04, and this is the entire serialized model. Let me just quickly show you what this guy has. Okay, so this was the serialized model. Okay, let me just. So this is the lr.zip file, and what you have here is the entire serialized model that's been serialized out. So let's see the. So we created the pipeline. There is the model.json file and the node.json file. The model.json file, let me just quickly show you on this. This is at the top level. And generally, the model.json file has your the coefficients, the intercepts, the mappers for your string indexes, the array indexes for one-hot encoders. And in this, let me also show you the linear regression just to show you the model. So as you can see here, you have the features. And sorry, this was the node.json. Let me show you the model.json. Yeah. So as you see here, you have the intercepts and the coefficients associated with the model. And the node.json is basically, it wires your data frame to your model. So you would see the input and the output columns. And that is how the mleap system would know what these input columns are and the output columns are, and both the node.json and the model.json wires your system together to the model. Right. So that's the model part. I moved this PySpark. Okay, this is still to show this. I moved the models into a separate folder called models here. And this is the same model that we have. And now what I'm going to do is try and expose this model out. So what you have here is mleap serving. And this server is just sitting there and waiting for HTTP requests to come in. So if you see the, oh, I'm sorry, this should be a little bit more, you can't see anything, right? Is it good, guys? Can you see it? A little bit more? Yeah? Okay, so what I ran was, I created a Docker, okay, before that I think I need to show you the Docker file as well. Is it visible? The Docker file is a pretty simple Docker file that I have here. In production, of course, you will be having more mappings there. The serialized bundle that I created a zip file out of this, and I created an endpoint so that the mleap server that I'm running can actually use this model and serve that model, right? So this is a Docker container. And once you Dockerize this model, it's a completely self-scalable system by itself. what I'm doing is I'm running that container, right? And I'm going to try and send a row of data Okay. This is the single row of data that I will be sending across. So you have the schema file that's associated with it, and you have the rows. So this is a single row that I'd be sending across to the model that I just now created out and serialized out. Okay. So the moment of truth. So we saw the frame. Okay. So what I'm doing is I'm sending a curl post message using the JSON file that I have, that's the single row of data, to the mleap server that's listening on this port. And we immediately have results on that, and we see that it's possibly not visible, but let's see a bit. It responded in 108 milliseconds. Let me just try again, and you could see that this is responded in 43 milliseconds. So there you have it. In Spark, we were getting 216 milliseconds for the same data, for scoring that, for a single row of data. And now we did this in 46 milliseconds. When they benchmark this in production, people have been able to get less than 11 milliseconds as well. It also depends upon your model, the hardware that's it's running on, and how you would want to expose those models out as well. But it is possible to get down to low millisecond numbers as well. But this is all running on my laptop, right? How do I scale it up? One of the ways that I can scale up is use cloud services. Now, I don't have any affinity for any cloud service provider. I'll show you a demo on both Amazon as well as on GCP. The advantage is you could actually use their managed services and expose the API out very quickly with very minimal effort. So the Docker container that I created earlier, I've uploaded this to a container registry. So in Amazon or when you are using Google Kubernetes cluster, you first have to upload all your Docker containers to a registry. I've named my container as KC for Kings County. That's the model that we created. I've created an endpoint configuration, and I've created an endpoint or an API that I can curl or basically send a message and get back the response from. Let me also show you the endpoint configurations a bit. The good thing about using something, a pre-built tool is you can actually create an A/B test out of your new model. You just have to create a new Docker container, upload it into a registry, and create another configuration here with an A/B test. You can create the instant type as well. If you think that you have more number of requests that are going to come up, you can have a higher instance type, a more beefier instance type. You can auto scale, and you could also create the weights. So say, for example, you want only a part of your traffic to reach this model, and if you are doing a canary deployment, you could use this feature to identify the weights that each of those Docker containers can get, right? So, and I've created this endpoint. Now what I'm going to do is basically send that same JSON file that we have. So this is the same JSON file that I have, and this is the endpoint, the Amazon SageMaker endpoint that I just now created. And what I'm going to do is basically send that same JSON file that we have there and send a post message. And so there you have it. The same Docker container that was on my laptop, I pushed it into AWS, and I exposed that as an API, and now I can send the messages across to the completely scalable endpoint. So that's that. This is Amazon. I also promised you guys that I'll show it on GCP. So what I did was I created a small cluster on the GCP terminal. I did the same process, uploaded my container to the container registry in Google, and exposed that as an API. What I'm going to do is basically send that same request to the newly endpoint that I created on Kubernetes. I'm using Apache benchmarked tool just to send the data, just to see if the endpoint can be scaled. And there you have it. We have a response time of the 99th percentile is 230 milliseconds. Let me try it again. And this was 197, and this is 188. So there you have it. I created the model on a Docker container. I expose it on Amazon using AWS APIs, as well as on a Kubernetes cluster that is on GCP. Let's go back to the presentation. So, coming back to the business use case that we started off with, the real-time classification of the user into buy versus differ in using anonymized feature. In production, I was able to get on 100 gigs of data that I created using Spark model on a very simple random forest model using anonymized features. I was able to get the data in, create an endpoint that could expose the model out in near real time, that is in 50 milliseconds. And the accuracy was 0.88. But what did I do to actually get that result? There's a very beautiful Rexus 15 winning paper that you guys might want to see. And this is specifically for clickstream. And the magic here is, because I was using a very simple model, there has to be magic somewhere, and the magic is in feature engineering, the simple, standard, old-fashioned feature engineering. And because clickstream data is very cyclical, you need to capture the seasonal points of each endpoint. And so I created, I can't show you the production features. This is from the paper, but there is one-to-one mapping between those features and what you can actually use in production. So you have the numerical time features, the categorical time features, and for each of those clicks, you create the unique items, the categories that they belong to, and the entire set. I'm not going to go through each of these features. The slides will be available to you. The paper is already available. You can go in more to dig further, and you can contact me if you have any questions later. So I just wanted to see if the results that I achieved in production was just a fluke, or is it applicable to all the external data sets. So Kaggle recently finished the Talking Ad Tracking for Detection challenge. I wanted to check if in this available data that I have, the anonymized data that's available on this challenge, how good is my simple random forest model with good feature engineering going to give? Because if I have a simple model, then I can scale up very easily. And I was able to, I did not win the competition, but I did get a very good result with 0.88 on the ROC curve there as well. So the 0.88 that I got on the ROC curve in production was not a fluke, and it seems that this features and the paper, whatever has been recommendation of the paper, it seems to be true. You guys need to try it again for your own clickstream use cases, and let me know how that goes for you. So the conclusion, data science is pretty much, it has entered mainstream very recently, but there was work going on for a long time. And so is computer science. You see these two parallel paths here. It started off in 1837 with the Babbage analytical engine. And in order to control chaos, the computer science has been fighting against chaos since 1837. And all these years, you see the ways, the steps that, the incremental steps that it has taken, and how we have approached and come to a more standardized way of doing software engineering. So in 2013, Docker came up. And in 2018, we are talking about Dockerized ML. This is not something that's overnight. It took a lot of effort in the computer science world to control chaos. Now in data science, it was coined, possibly the machine learning was coined in the late 1950s. Electronic trading started in 1987, and then the Black-Scholes got the Nobel Prize in 1997. So there was universal recognition that mathematics can make money. That is where everything ends finally, I guess. But if you see this path, 2018 is the year where you're getting more and more relevance for Dockerized ML. And the theme that I'm trying to tell here is once you can get your machine learning models in a Dockerized format, you don't have to reinvent all this pain that has gone through to get control chaos. You just, by using a Dockerized ML, Docker today is the currency that can map these two worlds together for you. And hence, you need not reinvent all that has gone in the computer science world. I would like to end this talk with an anecdote. So this comes from the book Art and Fear. The ceramics teacher came to the class one day and divided the class into two halves. The first half, she said, is going to be evaluated on the quantity. That's how she's going to, at the end of the day, she's going to get all the ceramics pieces, weigh them, and just on the weight. The other half, she said, is going to be evaluated solely on the quality. How good, the aesthetics, everything on a ceramics has to have. At the end of the day, what was found out was the highest quality ceramic pieces actually came from the group that was being evaluated on quantity and not quality. So why did this happen? It turned out that as the group that was being evaluated on quality were ideating on how best to design a particular ceramics piece, the quantity group were busy building ceramic pieces after ceramic pieces, and in that process learn from their mistakes and create better ceramics pieces. So what does this have to do with machine learning? Well, the simile here is data changes, the shape of your data changes, requirement changes, business changes, new model comes in. In order to make sense out of this, you possibly want to create models that can quickly go into production and quickly come out. Because like all good things in life, machine learning models also have expiry date. They too die. They are also not relevant after some time. And then we need to respectfully take them out of the production pipeline and allow them, the newer models, to come in, right? So that's been my presentation, and hopefully I could drive in the theme. And these are the few references that you have. And if you have any questions.
If I shout out.
Yeah, yeah.
You mentioned that you used MLeap, but you briefly mentioned that Databricks have sort of released their own version of it. But so if you could have your choice again now with that technology available, would you still choose MLeap?
MLeap has been particularly been driven for the real-time use case. DBML was an add-on. So yes, I would still choose MLeap. However, I need to track this space a little bit more, because there has been discussions between the founders of MLeap and Databricks, and there's a discussion to get this new technology into Spark world as well. So there's quite a traction going on. So if you go into the MLeap GitHub, you could actually see some requests there, and certain issues that have been used by the Databricks folks as well. Yeah.
How does the Apache Beam project relate to this?
Yeah, so the question is, how does the Apache Beam project relate to this? MLeap is a very niche product in itself. MLeap solves the problem of getting the data out of your Spark context into a structured form where you could use real-time scoring. It avoids the entire distributed tax that's the Spark has. And Apache Beam, it doesn't have yet anything that matches the MLeap space. So from a framework perspective, it doesn't compare with MLeap. You could compare Spark, you could compare Flink, but then not MLeap with it. Yep.
MLeap seems quite similar to maybe the rules of PML.
Sorry, could you please speak?
MLeap, it seems quite similar to PML in some ways. So PML has been around for a long time. So I'm just curious to know, like, is MLeap maybe a better approach than PML, or should we still consider PML?
Yeah. Yeah, PML is it's a format, I think, that has served its purpose well. It's completely XML based. I don't like coding in XML. I don't know about you. So MLeap is completely Scala based and JSON based. So, and also if you see the Spark models, not all MLeap models have support for PMML. Only a very few have, whereas in MLeap, you have support for all the transformers estimators. The caveat being, I think on ALS, still there's been worked on. But if you're talking about random forests, linear regressions, classification models, everything is available on MLeap today. Yep.
I'm just wondering how your solution might change if you're in an environment where you need to augment the data on the fly as it's coming in. It seems like here you've not really kind of gone into how data gets kind of turned into this nice feature vector. So I presume the data comes in and it's kind of ready to go, and you can do all of your feature engineering with what you currently have.
Indeed. So if I understand the question correctly, how do I build models in real time?
It's more like if you need to do augmentation of that data with like warehouse data and that old data from the past.
Yeah. Yeah. So please correct me on this. The question is, how do you get the old data that you already have and combine it with the real-time data and use the model to take advantage of both those data points? Is that right? Yeah. So what happens here is I showed you the Lambda architecture. You could have two models created. One model, a simpler model, that's been created, that's running on the real-time data that's coming in. And you could possibly have a more complex model that's been created on the batch data. Assign weights corresponding to both the batch model that has been created and the newly created model. And then in the pipeline, basically, you could have this API that calls at the application level both these endpoints and use a particular weight to identify, and as the data comes in, a score using both these models. Does that make sense?
Yeah, I think so. I guess so the second API is about doing this lookup over the batch data, is that what you're saying?
Exactly, yeah. Yeah, because once you create it in an API form, you could have not one but multiple API endpoints, and it's up to you how you combine these and assign weights to these endpoints to finally use it in the endpoint, in the application that's using the endpoint. Yep.
You sort of abstracted the model out by providing some REST support. So intuitively, it would feel ideal if you could have your app, which just makes a call to some sort of wrapper overflighting node of the model. So you could just plug it into your pipeline more directly. Any comments on sort of how latency might compare, or whether there are tools that allow you to do that?
Yeah, that's a very important point. So why not just expose that model in a Flask server as a REST API, right? One good thing is here, you could use, what you're seeing here is Scala code. I need not expose the model as a REST API. I could use the newly created model, I can wrap it in Scala code itself. In fact, the API server that I created, that is this is a completely Scala code that wraps the new model, and you can create a jar file and use that jar file directly in your JVM based if you have a more real-time use case. The reason I showed you the REST API was it would be much more easier for showing it in an audience, but in production environment, what you would have is basically wrap this inside a jar and then use your own application code to basically get the data. So that's the difference there. Does it answer your question? Yep. Any more questions? Yep.
Have you considered any in-memory compute solutions like Ignite for this?
Yeah, so the thing is, in my use case, I was fine in building the model, and it was fine building the model if it took a long time. Ignite it helps, Spark by itself is an in-memory, and you can beef up your machines depending upon how quickly you want to get the models out. And for my use case, basically, I had the luxury of building the model for one day, you know. So roughly when I built the model on my 100 gigs of data, it took me about 8 hours, and that was fine for the business use case because the model that I created was taking care of the seasonality patterns, and that gave me, so good feature engineering gave me luxury of building models a little bit, to take a little bit longer to build the models. So yeah. Yep. So that's that. Thank you.